Okay, welcome here. Last day. We're gonna finish up talking about a few more things in kinetics, and then we'll be done. We'll go to lab, obviously, and check out a lab. Then we'll be done at that point. And then obviously we have our final coming up here on Thursday. Okay, so in this last chapter, we started talking about kinetics. And again, up to what we talked about last lecture, pretty much is the only thing you're responsible for the final. So what we did talk about last semester, maybe last semester, the last week, was the idea of the rate. And typically in kinetics, when we talk about the rate, a lot of times we look at molarity, say per second, and again, it's usually a unit of concentration over time, or how the concentration is changing with time. One way that we can kind of look at how reactants and products are changing with time is to look at what's sometimes referred to as the rate expression. And the rate expression can be basically written from any sort of balanced equation. So if we got something like this. Now, when we do this, we could say that the rate equals, remember here, we do want to take minus because A is a reactant. And we also want to do 1 over the coefficient, as that will take care of our kind of mole-to-mole relationship, the stoichiometry that's involved, the change in the concentration. Write that right. Try that again. Go ahead of the change in the concentration of A over the change in time. That also equals minus 1 over B, the change in the concentration of B over the change in time. Also be a reactant, so it should be decreasing with time. When we do get to our product side, though, it is increasing with time, so we would expect products to be made over time. So we do not do the negative. So it will just be 1 over the coefficient, the change in concentration of C over the change in time. Now, again, you can set all these guys equal to each other, which is sometimes referred to as the average rate. A reminder that when you do calculate the sort of average rate for a reaction, usually is a positive number. And that is essentially why we also have the negative values here for our reactant, because when we do say the change in the concentration of A, that is really the final concentration minus the initial concentration. And because the final concentration should always be lower than the initial concentration, we started with, say, 4 molar and ended with 3 molar, that will obviously give us a negative number. And that negative, along with the negative that's there, will turn the rate into a positive number. That's not needed for like our products, because our change in the concentration of our products should really always be a positive number. Again, here, we started with 0 and we ended, say, with 2 molar. So 2 minus 0 obviously gives you a positive value. We can set each of these things equal to each other. We could just pull out the parts that we need. If we were interested in just 2 parts of it, we could set them both equal to the rate. So for example, the rate is equal to minus 1 over A, change in concentration of A over change in time. We also can just pull out the product guy there as well. And a reminder, what really ties them together is the rate. These are really the same number here. And that's why in this sort of calculation or something like this, if you pretty much just know one piece of information, either the overall rate, the average rate there, how a reactant is changing with time, how a product is changing with time, you basically could use these relationships to figure out how everybody is changing with time. Overall, the average rate for the reaction should be a positive number, but if you were asked to calculate in a couple examples that we did, for example, how a reactant is changing with time, you will end up with a negative number for that guy. And just like if you were interested in just how, say, a product, the guy in the box there, is changing with time, you will end up with a positive number. So the average rate overall is a positive number, but individually for reactants, they will usually be negative numbers for how they are changing over time, and products will be positive numbers. Any questions on that there? Now, as we talked about, this is sort of the average rate, and we talked about sort of average rate and instantaneous rate, and over the whole entire reaction, right? On average, everybody is changing by a certain rate, which is sort of what the average rate is. But individually, some may be changing faster than others. But when you take everybody as a whole, you get sort of that average rate, and some may be changing just like the average rate is as well. We talked about that there is also a rate law is another way that we look at sort of kinetics. And the rate law has a general formula of something that looks like this. And the rate law is a little bit different than sort of the rate expression. The rate law is a couple of things. It only deals with reactants. So no products in the rate law. It also is found experimentally. And remember that K here is what is referred to as the rate constant, and that is lowercase k. These are obviously concentrations, which is molarity in most cases. And X and Y are what are referred to as the orders. And they also are found sort of experimentally. They are not the coefficients in the balance equation. So again, we typically are given in these type of problems a table, and in that table you usually will have some concentrations of the reactants. You'll also have some initial rates given to you. And remember that you may have one, you usually will have at least three, but you may have more. But you'll have several entries into this table. And the goal here is we can mathematically sort of figure out the orders by using sort of this formula that the rate 2 over the rate 1 is equal to K times A to the X and B to the Y divided by K, A to the X and B to the Y here. The 1 and 2 here, again, doesn't mean that you necessarily go to the table, grab number 1 and 2 out of the table, but it basically means you want to go to the table and find two entries where one of the reactants remain constant. So let's just say this guy was 4 and this guy was 4. And one where the concentration sort of varies for the other one. So in this case, you would perhaps choose this, and you could do something like the rate was 8 and 2. So in this case, we would grab this information. This will allow us to solve for the order of A. As I mentioned before, you don't have to do this, but a lot of times when you do pull sort of those numbers off the table, if you kind of put the one with the larger rate up on top, you usually will get a little bit more nicer whole numbers than if you kind of did the opposite way. You eventually will get something like, 2 to the X is equal to 4 or something like that when you put it into here. And again, to really solve this, you can just look at it in this case that X would be equal to 2. But again, you could also natural log both sides there. And basically when you do that, you'll have the natural log of 2 and the X will come down, natural log of 4, and you can just divide the natural log of 2 to the other side and you end up with the same answer. So if you don't get really maybe pretty numbers or something like that and nice whole numbers that you can maybe just visually look at and see it's like a 1 or 2, whatever it may be, you basically natural log both sides and divide it out. What do the orders sort of help us understand? It does help us understand sort of how it affects sort of the rate of the reaction. I think we did a couple examples where, again, if you have, say, the rate is equal to K, and both of the orders here were first order, which means overall the reaction would be second order, and that is found by adding these together. It gives you the overall order for the reaction. Again, if we just kind of put made up numbers for concentrations in here, we would end up with something like 4 molar seconds as, say, our rate. If we double the concentration of A, for example, in this case, it started with 4 molar and kept the other guy constant, we would then end up doubling our rate. It would go from 4 to 2 by just doubling that concentration. We also could half the concentration and would slow it down by half as well. Now, that would be different than if you did have, like I maybe looked at an example where say this guy was 1 and say this guy was 2. If we started with just the same 2 molar concentrations there, 2 squared is 4, 4 times 2 is 8, say, molar seconds. So even though we're using the same concentrations, because the order here is different, this reaction is going to actually occur twice as fast because of B's concentration, basically. And that would also mean that if I really did want to kind of slow this guy up, I probably should attack this guy, lower its concentration. Say I lowered it to 1 molar. 1 squared is 1. 1 times 2 would be 2. So in this particular case, by having the concentration of B, I was able to slow down this reaction, by a factor of 4, basically. So again, practically speaking, this is sometimes very good information to know, especially if you're doing some type of experiments and you're trying to do some measurements and maybe it's just occurring way too fast for you to measure. You can play with the concentrations if you understand the orders, and you can really sort of dial in how fast or how slow the reaction may take place. Yeah. Not necessarily. You could. It depends on what you would want to do. So, for example, if we went over here and we doubled the A in this case, that would be 4 for the A, and we kept the B still at 2. We still have 2 squared, which would be 4. 4 times 2 would be 16 molar seconds. It did increase the rate, right? But it only increased it basically by doubling the rate, by just doubling that reaction, which may be fine for what you want to do, as opposed to if we doubled B, which again gave us, if we doubled B's concentration to 4, 4 squared would be 16. 16 times 2 basically would give us 32. So it would go up by a factor of 4 by doubling that one. So by doubling B, because its order is second, you actually see a much greater increase in the rate of reaction. But you could still definitely get an increase in the rate of reaction by, as you can see, they're just doubling A's concentration. So you don't have to necessarily always do the second guy. But if you want sort of maximum impact of like either speeding it up or slowing it down, probably somebody with a higher order would be the one that you would want to play with, because that's really the one that's going to be really affecting the rate more than the guy with the smaller order. And if you even have an order, by the way, if we ended up with, say, something like this, when you take something to the 0 order, it equals 1, right? So basically, if you had this as your rate law, you could do whatever you would like to A. In this particular case, it will never have an effect on the rate because it's to the 0 order. So the only way to get any type of change in that reaction would be you would have to go with that guy in my case. Yeah, so you could have, very common sort of exponents, 0, 1, 2. A lot of times we don't really get into like 3, 4, or 5, really large numbers. Because really most reactions, if you think about sort of overall orders, for example, when we added the overall order, this one's like second order, most reactions that you've probably seen, the number of reactants that you have is usually maybe 1 or 2, right? You very rarely see a reaction where you got like 3 or 4 things reacting all at once, right? It's usually like 1 or 2, which means in most cases, if they both are first order, second order reactions are very common. You could have one that is 0 order, one is first order, so first order type reactions, or even ones that are 0 order reactions are very common. So really high orders of reactions, overall orders, are less common, because in order to sort of achieve that, you would need probably a lot more reactants sort of reacting at once. So as we'll see a little bit here, 0 first and second order overall reactions are very common type reactions because of that, because usually it's either 1 reactant or 2 reactants sort of happening. Other questions on that? Okay, so let's do another one of these just to make sure, because this is stuff that is technically could be on the final, maybe. So you don't miss that question that's on the final. That's like this, yes. All right, so let's take this here. Let's calculate the rate law. Let's figure out the orders. right? The value of the rate constant and the overall order of this reaction. All right, based on this table of information. What's that? It might not, it might have been a late ad. It might have been. Okay, let's take a look, see how you're doing. So we can start with just sort of the generic rate law here for this reaction, which would be the rate is equal to K. Remember, it is only the reactants involved. So we'll call this guy to the X. And we'll call the CO here to the Y. So again, we want to really go to this table. And as we mentioned, find two entries where we keep one of them constant, the concentrations, and we vary the other. So there's a few different ones you could sort of approach, but it looks like number 1 and number 2 will keep the CO constant and vary the NO2 concentration. For me, I'm going to do the rate 2 over rate 1, and I'm going to put experiment 2 up on top since it does have sort of the larger rate value. So again, what I'm going to do is look at experiment here 1 and 2. And it's going to be our rate there up on top. And again, everything for experiment 2 there will go up on top, which means we would have K times our concentration of our NO2, which would be 0.2 to the X, and our concentration of CO, which would be 0.1 to the Y. So that is all the information here from experiment number 2. Experiment number 1, we're going to put there on the bottom. So that would be 0.0021 K, 0.1 to the X, and 0.1 to the Y. At this point, we could do a little dividing action here. We'll take 0.0082 divided by 0.0021. That's going to give us like a 3.9048. Now on this side, this is the rate constant, which means a constant number, although we don't know it right now. It should cancel out. When these cancel, that actually gives us a 2 to the X. And these guys should completely cancel, as Y should be the same for the top and the bottom. Again, although we don't know it at this point. If you want, you can round that to 4, and you will see that basically X is equal to 2. If not, then you would take the natural log of 3.9048 equals the natural log of 2X. Again, when you take the natural log of 2X, the X does come down to just being X. We then essentially will take the natural log of 3.9048 divided by the natural log of 2 will equal X. And if we take the natural log there, both of those guys, and do a little dividing, will get us basically that X is equal to 1.97. And I'm going to call that close enough to 2 for my taste there. Any questions on that there? Yeah. Yeah, you could. It will really come out the same, as you can see here. If you round it up to 4, then you could probably visually see that it would be 2. But this technically is sort of how you would get sort of to 2 correctly mathematically. All right, so now that we know the order for NO2 is second order, we then want to go back to our table and choose 2 other entries, where in this case the NO2 stays constant, and it looks like it will be number 2 and number 3 will do that for us. That will keep this guy constant. So looking at experiment 2 and 3 here, I'm going to pick this guy and put up on top. So 0.0083 equals K, 0.2 to the X, 0.2 to the Y, divided by all the information number 2, 0.0082 K, 0.2 to the X, and 0.1 to the Y. In this case here, pretty much a 1 in that case, just a little bit over 1, but pretty darn close to 1. So you got basically 1.01, which again, at this point, I'm just going to round to 1. And coming this way, those guys should cancel. These guys should completely cancel. And this would give me a 2 to the y. So as we just talked about, right, y would equal 0 in this case, right? And you would get that if you took the natural log of 1 on the left there and then divided the other guy over, would get you to 0 as well. Or if you did, I guess, 1.01, you might get a slight number there, but basically 0. So that means that the orders here, we could actually complete our rate law. So our rate law would actually be K NO2 was to the second order. And really, because this guy is 0, you could either put it in, and you do need to make sure you put the 0, or you can just leave it out. So you could leave it out. Or if you did put it in, you want to make sure that you do put, I don't run that around there. Let's go this way. Rate is equal to K NO2 squared and RCO. You want to make sure that you do put the 0 there. Otherwise, if you don't put the 0, you leave it blank, it means it's an order of 1. Yeah. So again, that's your 2 options. Probably the better option might just be to just write it like that, so you don't accidentally leave it empty and stuff like that. At this point, once we do have the completed rate law, the overall order of this reaction would be adding those together. So that would be 2 plus 0, which means this is a second order overall reaction. And we can now solve for the value of K by taking our rate law and solving for K. And we do that by dividing the NO2 to the other side. And we also want to make sure that we are still squaring it at this point because of the 2 that's there. And at this point, as we talked about, you really can choose any entry you like from the table. You just can't mix and match, so you can pick any one you want. I'm just going to pick the first entry. So that means our rate is 0.0021 molar seconds divided by NO2, which is 0.1 molar squared. And that will get us 0.0021 divided by 0.1 squared. Looks like 0.21. The units here, molarity up on top and 1 on the bottom will cancel. Will give us basically 1 over molar seconds. Also sometimes written m to the -1, s to the -1, same thing. You can, but it can, because the exponent is 0, whatever number you put in there will end up as 1, basically. Yeah, so it doesn't really matter. You can either put it in or not, but it'll end up as 1. Other questions? And these are the typical units that we see for a second order reaction overall. Now let's try one more here to wrap it up for this part. It's equal to K. We'll call the NH4 plus X. Call the NO2 minus Y. Y, maybe Y-ish. Pretend that's a Y. There we go. All right, so looking at our table here, looks like we could do 1 and 2. We'll keep that guy constant there and vary our others. So experiments 1 and 2. That will give us the larger rate over here, and that would be, by the way, 32.3 times 10 to the -7. You should not forget that part there. If you did forget that part, you'll be okay at this part, but later on, you will not be okay. K would equal our 0.06 to the X and our 0.2 to the Y. Gonna put all of our numbers here for number 1 on the bottom, 10.8 times 10 to the -7, our K 0.02 to the X, 0.2 to the Y. So taking our top guy divided by our bottom guy, gonna give us basically 2.99, I believe, which is pretty close to 3. That is going to be K's canceling out. These guy here will give me 3 to the X, and those guys there will cancel out completely, meaning in this case, X will equal 1. Any questions on that one there? Now, varying our first reactant, I'm sorry, keeping our first one constant, and varying our other one will be 3 and 4, who do that for us. Experiments 3 and 4. Once again, here I'm going to go with the higher guy up on top. That's going to be 21.6 times 10 to the minus 7. Okay, 0.2 to the X, 0.0404 to the Y. Putting number 3's info there on the bottom. And again, 21.6 basically divided by 10.8. Going to give us a 2. These guys will cancel, and this will give us a 2 to the Y, where Y here would also equal 1. That means our completed rate law here would be the rate is equal to K times NH4 plus and NO2 minus, each one being first order. And that means that the overall order of this reaction would be 1 plus 1, which would be second order by adding the orders together. And now that we have it, we can solve for our value of K, which in this case, K would equal the rate divided by the NH4 plus concentration and our NO2 minus concentration. Now, this would be the part where you will be off if you missed that right there in the table. So I'm going to take number 1, which is 10.8 times 10 to the minus 7 molar seconds, divided by 0.02 molar and 0.2 molar. Molarity up on top and bottom will cancel, and we will get 10.8 to the minus 7 divided by 0.02 divided by 0.2. Going to give us 0.00027. Again, the units here will be 1 over molar seconds. Any questions on any part of that there? All right, so again, it was up to this stuff like we did last time that you are responsible for. Should it show up there as like the last question on the exam? I don't know. Should it show up there? Make sure that you know how to do it, I suppose. No, I'm going to take it off now. I'm just saying now. All right. All right. Any questions on any of that stuff there? All right, let's just talk about a couple other things here because I feel like we should. All right. So let's talk about some specific orders of reactions and some rate laws that go with it, some graphs to go with it. Let's talk about first order. First order kinetics is sort of an important type of kinetics. It is the ones that obviously are for first order reactions. But if you take 200B, you will again see these guys in the nuclear chemistry chapter, because all radioactive decay basically follows first order kinetics. So we do see it a lot, and you will see it again if you take the second half of the class. So in order obviously to get a first order reaction, there's really one of two ways. You either have obviously one reactant that is first order, or you could have two reactants where one is zero order and one is first order, right? So that's the way you could obviously have two reactants to get you there. That gets you a rate that looks something like this, where the rate is equal to the rate constant times the concentration of A. And if you do solve for the units of the rate constant, these are the typical units that we see for a first order reaction. And it is basically 1 over some unit of time. Although a lot of cases it is 1 over seconds, because if you think about reactions that you do, you usually don't run reactions for hours, days, weeks, years, and stuff like that. You know, you usually time something over a period of seconds and stuff like that. Like you did the other day when your thing eventually turned blue when you looked away, right? You were timing how many seconds it did that. So why that's important is different orders of reactions will have different units associated with the rate constant. And very often they will not like tell you, hey, in blinking lights, this is first order type reaction. They will give you the rate constant with the units and expect you to know that it's like first order based on those units. So 1/seconds or reciprocal seconds, very common, but it could be anything, 1/minutes, 1/hours, 1/days, anything like that. So there's really two sort of graphs that are typical for a first order. And if you graph the concentration of A versus time, because A is a reactant, we would expect it to do what we see here, decrease with time. But a lot of kinetics sort of graphs and stuff like that is basically sort of the linear relationship that you get. So if you go through this guy and do a little integration, this is what is sometimes referred to as the integrated rate law for first order reaction. And that is the natural log of A. And this is kind of like your final concentration equals the natural log of A naught, which is like your initial concentration. K is your rate constant. And actually, T here is time, not temperature. So it's actually time in this case. And if you rearrange that integrated rate law to the natural log of A is equal to minus KT plus the natural log of A naught. This is written in the form of a straight line, where this is Y is equal to MX plus B, which is how we get this straight line right there. And that is why we graph on that graph the natural log of A, which is what Y is, and X is time. And if you do that, you will get a linear relationship that occurs where the slope of that line will actually equal minus the rate constant. So graphically, if you had the numbers, you could kind of graph it. You can get the slope of the line. Should give you a linear relationship if you're dealing with a first order reaction, and you can use that to figure out the rate constant. There's also another equation that goes with this integrated rate law, which is an important one, and it's actually the half-life equation. The half-life for a first order reaction is the natural log of 2 over the rate constant. And if you do the natural log of 2 on your calculator, that's a 6.93 divided by K. So a lot of times in kinetics, you do use sort of these numbers or formulas together. The half-life is the time it takes for half of whatever you got basically to go away, right? So if you started with 10, after the first half-life, you have 5. After the next one, you got 2.5. After that, I need a calculator, but you keep dividing by 2. And there's a certain period of time that it takes for that to occur. So for example here, why don't we try one? The reaction of 2A goes to B. It's first order with a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds at 80 degrees Celsius. How long will it take for A to decrease from 0.88 to 0.14? So let's take a look at this here together. We know it's first order because they told us it's first order. We would also know it's first order because they gave us the value of the rate constant units, which are reciprocal seconds. Basically, what that tells you is you should use the first order integrated rate law here, which is the natural log of A equals natural log of A naught minus K times T. We have K given to us, which is 2.8 times 10 to the minus 2 reciprocal seconds. We have our initial concentration, which is 0.88 molar. We have our final concentration, which is 0.14 molar. And in this case, we're actually looking for time, how long it's going to take. So we really could just plug our numbers into here. The natural log of our final 0.14 equals the natural log of 0.88 minus 2.8 times 10 to the minus 2 reciprocal seconds equals time. Personally, for me, the way I would do this is I would take the natural log of 0.14, then subtract the natural log of 0.88. Or you could do the math relationship where you divide it, whichever way you like to do it. Natural log of 0.14 minus the natural log of 0.88. That gives me minus 1.838279 equals negative 2.8 times 10 to the minus 2 reciprocal seconds times time. We're going to divide this to the other side. We also want to make sure we take the negative with it. And we will end up with a time that is about 66 seconds. So within a minute, this reaction will drop concentration from 0.88 to 0.14. Any questions on that there? By the way, mathematically, when you do the natural log of something minus something, that's like dividing, right? And that's how the molarities cancel, technically speaking. That's sort of how they go away, and we're left with seconds. That is there. Any questions on that one there? So as I mentioned before, the half-life equation for a first order reaction is the natural log of 2 divided by K. And again, it is that time it takes for half of whatever you started with basically to go away. As we see here for our first half-life, second half-life, fourth half-life. By 10 half-lives, you don't got much left over. So let's talk about some other orders of reactions, why we have them here. Another very common sort of order of reactions is a second order reaction, and a second order reaction can be achieved a couple different ways, like we did in the previous problem. You could have one reactant that's second order, one that's zero order. You could have just one reactant that's second order. You could also have two reactants where they're each first order, will give you a second order overall sort of reaction. When we solve for the rate law for K, we get the units that we saw in a number of those examples, which again are the common units associated with a second order, which is 1 over molar seconds. It has a different integrated rate law, which is actually 1 over A. So this is 1 over our final concentration minus 1 over equals 1 over our initial concentration. And the rest here is the same. So that's our rate constant and our time in this case. As you can see here, it has a little bit different half-life equation because it is second order. It actually is 1 over the rate constant times the initial concentration. So in this case, the initial concentration does play a role in the half-life of a second order reaction. So again, the kind of larger one that you have here will affect obviously the half-life as you're dividing, but you are taking 1 over it. So it's actually opposite of what you might think. We also could rearrange this guy and solve it as a straight line sort of relationship, and it is this, where y is equal to mx plus b. Here we would graph 1 over the concentration of A on the y, on the x would be time, will actually give us a positive slope line here. And in this case, the slope of it will equal K. So this is why it's important to understand sort of the units associated with K, because if it is second order, you would want to obviously use the second order rate laws here rather than the first order. And the last other sort of common type of reaction is zero order. And as we saw there, you know, a zero order basically equals 1, which means that the units associated with a zero order rate constant is actually the same units as you see for the rate, is molarity over seconds. And it also is dependent on the initial concentration, the half-life here. It is the initial concentration divided by 2K. And we have a rate law that looks just like the first order, except there's no natural log action happening there. And again, you could rearrange this and solve for a straight line by rewriting it like this. Y equals mx plus b. So our linear relationship is we graph the concentration of A on the y, time on the x will give us a linear slope. Where it is negative will equal the rate constant. So this is in a kinetics experiment, a very common thing that's sometimes done. You run a bunch of experiments, you get a bunch of data, and you basically do all these 3 typical linear graphs. You graph the first order sort of plot, you graph the second order plot, you could graph the zero order plot, and graphically you can use whichever one has the linearest line by using the r squared value, right? A little linear regression, one closest to 1 is most linear, right? you could sort of graphically determine, what the overall order of your reaction is by doing an experiment and actually doing graphing. Any questions